Yeah, good afternoon, and welcome to the 7th week of facilitation. Gradually, we are getting to the end of the class. So by next week, we should call it a day and wish you best of luck in your forthcoming examination. So today, we shall be looking at imperfection in solids. But before we proceed, is there anybody that have any questions concerning what we have discussed so far? So that we look at that before we move to the next thing today. Any question? Okay. In the absence of no question, so we start straightforward. So imperfection in solid. So what do we mean by imperfection in solid? We shall be looking at defect, more or less they call it defect, which is same thing as imperfections. So if this defect occur, what happens to solid materials? And what are the types of defects that we have in solid materials? These are the things we are going to be discussing from today till next week. So we say crystalline structure that we have looked at have imperfections. So the common point imperfection in crystal are chemical impurities, vacant lattice sites, and extra atoms not in regular lattice position. We have linear imperfections are treated under dislocations. So the crystal surface is a planar imperfection with electron, phonon, and magnon surface state. So when you talk of imperfection in solid, for example now, if you look at the wall are arranged based on the brick laid together to make the wall. But if we try to remove one of the brick from the wall, you have created a vacant position. So that vacant position can be referred to as imperfection in that wall because you have technically introduced an empty space along the rays of the blocks used to mold the wall. So this is a typical example of what we call imperfection in solid. And if we have removed it, let's say we remove that block and we use a clay block to replace that. So we have introduced an impurity because that clay block is different from the one they use at the initial stage of mounting the wall. So that clay block now is what we call impurity in science or in the study of solid materials that have to do with defect. So now, crystalline defect. A crystalline defect is a lattice irregularity having one or more of its dimension on the order of an atomic dimension. There are 5 major categories of crystalline defect. One, that is zero dimensional, which is called point defect. We also have one dimensional, that is linear defect, which is also called dislocation. Then we have two dimensional, that is planar, that is on the surface. And another one is the 3 dimension, which involves the volume. Then the last one is vibrations. So we start one after the other. So we first look at point defect. There are 2 main types of geometrical defect in crystal. There are those which are very localized and are of atomic dimension. These are called point defect. An example of this is an impurity atom, which can be either a substitutional or an interstitial impurity. What we are trying to say is that in point defect, it's either you put an impurity into the system, like what I said the other time, that a brick, you put a red brick inside the wall of a fence. So, but in physics or in material science, for example, we have a silicon crystals that has 8 atoms. So if you remove one of the atoms of silicon and you replace it with boron, so boron in this position is an impurity and is a kind of a substitutional element which has replaced silicon. You take away silicon and you replace it with boron. So that is a kind of substitution, that is, you are removing one and using another one to replace it. So another thing is that when you have interstitia, meaning that when you arrange the silicon atom, they are in a kind of an array. So when you now take one from that positions and move it to another positions, so you have technically introduced what we call interstitia. So when some atoms are not exactly in their right place, the lattice is said to contain imperfection or defect. Many properties of solid, e.g., the electrical resistance of materials or solids, the mechanical strength are governed by the presence of certain types of defect in the lattice. So point defect allow for diffusion to occur in the solid state. There are different categories of point defect. One, vacancy. So in the case of vacancy, this is just taking away an atom from a system without replacing it. You have created an empty space. So it's called vacancy. These are produced by thermal vibration of the crystal lattice and or from need to maintain charge neutrality. Another one is self-interstitial or interstitiality. So a position on the crystal lattice that is not normally occupied is called an interstitial site. If it is occupied by the same atomic species, it is a self-interstitial or a self-interstitiality. So it creates large distortions in the crystal lattice, and so the concentration are small. So another one is impurities. Solid solution, homogeneous single-phase material that are completely analogous to a liquid solution, that is alcohol or water, solute, solvent and solubility, which is miscibility. Random solid solution versus other solid solution. These are examples of impurity in the materials. Now, all this can lead to, we also have what we call Schottky defect. So it's a pair of oppositely charged ion vacancy. We also have Frenkel defect, which is a vacancy interstitial combination. So now, we also look at linear defect, which is dislocation. Unlike point defect, these are types of disorder which extend beyond the volume of one or two atoms. It is a line defect which can extend right through a crystal, or it can form closed loop. A line defect is a lattice distortion created about a line formed by the solidification process, plastic deformation, vacancy condensation, or atomic mismatch in solid solutions. So dislocations explain the observation of plastic deformation at lower stress than would be required in a perfect lattice. They also explain the phenomenon of work hardening. There are two basic types of dislocation. We have the edge dislocation and the screw dislocations. Any question? Okay. Now let's explain the concept of edge dislocations and screw dislocation. These are caused by the termination of a plane of atoms in the middle of a crystal. In such a case, the adjacent planes are not straight, but instead bend around the edge of the terminating plane so that the crystal structure is perfectly ordered on either side. The analog with a stack of paper is apt. If a half pieces of paper is inserted in a stack of paper, the defect in the stack is only noticeable at the edge of the half sheet. We can see that in this figure. Look at this figure now. This is what we're trying to say. You look at this picture, see that you have, if you start something here, you see that it is only at the edge that we can see a kind of different in the arrangement. Is that taken? Okay. So screw dislocation, now this is more difficult to visualize, but basically comprises a structure in which a helical part is traced around the linear defect, that is dislocation line, by the atomic planes of atom in the crystalline lattice. So you can see also in this picture, this is a screw dislocation, that is a kind of shift in the arrangement of the crystals. Now let's look at planar, that is interfacial defect. In this case, we have external surface, grain boundaries. So in the case of external surface, atoms at any surface are not in their perfect crystal positions because they will have decreased number of neighbors than the atoms inside the volume of the material. Hence, these atoms will be at the higher energies. During solidification, materials try to minimize this. Then grain boundaries. Grains are formed during the solidification process. A grain boundary is the area of mismatch between volumes of material that have a common orientation of the crystallographic axis. So the atoms at grain boundaries are not in their perfect crystal positions. and hence the grain boundary is less dense. These atoms are at higher energy than the atoms inside the volume of a grain. The thickness is of the order of 2 to 5 atoms wide. There are different categories of grain boundary. We have the low edge tipped boundaries, that is a few isolated edge dislocation. We have the high angle tipped boundary, which is more complex. At ambient temperature, grain boundaries give strength to a material. So in general, fine-grained materials are stronger than coarse-grained ones because they have more grain boundaries per unit volume. However, at higher temperatures, grain boundaries hard to weaken a material due to corrosion and other factors. Grain size can be quantified by grain size number, average grain diameter, and grain density. The size and shape of grains are determined by numbers of factors during solidification. They are one, lot of nucleation site, which is fine grains, fewer nucleation site, coarse grain, equal growth in all directions, which is equal axial grain, thermal gradient, that is elongated or columnar grains, slow growth, coarse grains, and rapid growth, which is fine grains. So most materials are crystalline or polygranular. There are some applications where the expense and time to produce single crystal materials and hence no grain boundaries is justified. Turbine blade, silicon wafer chips, twin boundaries, a special type of grain boundaries across which there exists a mirror image of the crystal lattice. It is produced by mechanical shear stress or annealing some material. We have stacking fault. The interruptions of the stacking sequence of closed pack plane. Phase boundaries. The surface area between the grains is a multi-phase material. Then we have ferromagnetic domain wall, the boundary between the regions that have a different orientation of magnetic dipole. So any questions so far? Questions? If you have any question, you are free to ask. Okay. If there is no question, so I think we stop here. Then we continue from where we stop next week and round up the class for these sessions. So thank you for coming.